Thanks. So hi everyone. I would like to talk to you today about rounding errors in finite element kernels. So it's slightly off topic for many people here, and this is a joint work done in our group in Luxembourg. So that's me, Paul, Andreas, with the collaboration of Matteo, who is at BCAM. So I start right with the FEniCS code. So imagine I want to assemble the following operation that would be an integral of some function u. And so I define a function u, I give it the value 1/3, and I will write the following kernel, which is basically an integral of u, and I add a huge number, and then I subtract from it. The huge number being 10 to the power 16. Right, so what do you think the outcome of this assemble operation would be in FEniCS? Well, for those of you who know floating point, maybe you see where I'm getting, right? But maybe you're also thinking, the form compiler isn't that stupid, right? Right? So we should run it. Yeah? So indeed it is. In this, and it will give us something which has a relative error of 10 to the 16. So the assembled volume of that function wouldn't be 1/3, but it would be 0. So now you can think, okay, so let's play with it a bit. And all I will do is I will add the compiler flags, and I will now compile this form with the fast math. So this is instructing C compiler to do something at the code. And now you're thinking, wait a minute, but I was told that the fast math makes the accuracy even worse, right? Well, not in this case. In this case, I would get that the assembled value would be then actually spot on what I want to see. So this would be 1/3. Then again, so this is interesting. So let's just change for a while, and instead of a function, I would just put there a literal 1/3, right? So I would not have a FEniCS function plus a big number minus a big number, but the literal float, and everything else is the same. And what would be the outcome now? And now you're thinking, how should this change the result, right? And now I get the 0 again. So something very flaky is going on, right? So it would be good if we can understand it. So if we look at this specific example, what happened is that if you look at the generated code, the function, in the first example, basically, you would see that there is a huge number added to the function w0, and then it's subtracted, and this code is basically executed instruction after instruction, and this is where the cancellation happens. So you round away the function to the big number. In the second case, however, the fast math includes the associative math operation, which breaks the associativity of the IEEE standard, so it's able to implicitly subtract large constants, and then it's doing the right thing. And in the last case, if I put the literal 1/3, it's actually the Python that will evaluate and will do the rounding there. So there is even nothing to assemble, like there would be, the form would say it's none or 0 or whatever, right? Okay, so this is pretty complicated, and we would like to understand, can we say something about these errors, right? Can we have some guarantees as a FEniCS users what these errors could be? So here comes the James Wilkinson to the rescue. So I'm going to be implementing basically what's called a running error analysis, which is this observation that was done in the very early computers in 1940s and 50s, that basically you can take an existing program, and just by observing its value, you can use the standard model of floating point arithmetic, and to every simple operation, you could, on a side node, keep the bound of an operation that's being computed. So we use the fact that we are working with machines that now satisfy, thankfully, the standard model of floating point arithmetic. That was not the case like before IEEE standard was established. And we have the guarantee that every operation has a relative error of delta, while the delta is not more than the unit in the last place, which is roughly this, what we know, like 10 to the minus 16 at the double precision, right? So this is our relative error of every operation. So what we can do is then we can basically bound the error of every operation, so that's the y hat, to the true result. For the triangle inequality, this composes like the new rounding error of the operation plus whatever the sensitivity of the incoming error is. And then you can work out the simple rules on how do I propagate the error through a finite element assembly program. And here I worked it out for example, for addition of two numbers, right? So the error in the addition of a plus b, the a plus b, is then the machine epsilon, so this 10 to the minus 16 times the value of that addition of two numbers, plus whatever the errors were of incoming A and incoming B. And you can work these rules for whatever operations you have. So whatever you would see in the FFCx generated kernel, like addition, multiplication, some basic math functions. There's not much else going on down at the C level. This is nice. So how this works is that you have, basically you keep the value of the result, and along that you keep also the quantity, which works as an error bound of that result. And there's this tuple of values that you propagate through the program. And this reminds you, this is kind of like a dual numbers implementation. So you get the value and the derivative, but here it's not a derivative, but it's the error bound or some sort of error approximation. So this is nice. You can keep an existing program. It's not that expensive. You just have a few flops per operation. And the bounds in this mode are rather pessimistic. I mean, they can only accumulate, but we will fix it later. So how we implemented that? We wrote this little extension library, FFCx backends, which all it does, it takes your UFL form, and it compiles that into C++ code, which is then templated over the data type that you assemble for. So now we can pass any data type there. And then we have we use a just-in-time compiler for the C++, the CPPYY. And now we can pass arbitrary type there, t. And you see where I'm going. I want to replace t from being double to being this kind of tuple of things that have a special arithmetic rules. And that special type, we have a new type that's we call the running error type. And that basically, here is an example how that operation of a product of that thing with another kind of that thing would look like. So the value is just the product of two values, and then this is the running error theory bound that you get. And then we have two modes. So the worst mode is a guaranteed upper bound on the result, and the exact mode is a signed approximation to the error. So we even have a more expensive way that you can compute the error using higher precision libraries. So this is more expensive, but it will give you more better estimate of the error, not like a very pessimistic one. Okay, and then we have some magic how to map this to the Python for convenience of the users. And if I go to how the interface looks like, so you can take an existing compatible UFL FEniCS form. So normally you would say FEniCS form to compile it, and then you would assemble it, right? For example, to vector. This is the standard interface. And now we can just say, Dolphin, this is the library where we implemented this. So I will just compile this into my custom form, and I will assemble it into a vector. And you will get, as a nice outcome, you will have into the real component of that vector will be the value, and in the imaginary part you will have this approximation of the error. So this works for arbitrary UFL form that you are currently using, being scalars. So 0 linear, 1 linear, or bilinear forms. So this has no limitation in what kind of problems you are solving right now. Okay, and I have one practical example to show why this is important. Like rounding errors are maybe a bit esoteric, but so here I'm considering the neo-hook hyperelasticity. So this is a simple 2D cantilever. You see the boundary conditions. And what I'm going to do is I will compute some reference solution, and I will be just interested in evaluating the strain energy function for every cell, like just to evaluate the strain energy function. And if you would have a look at what happens there, is that you have certain sub-expressions which experience what's called a catastrophic cancellation in the regime of small deformations. So now if I go to regime of small deformations, which is where the referential deformation is much, much smaller than the length scale of the domain, then basically for the deformation gradient, I'm adding an extremely small number to identity. So I'm rounding away many, many digits just when computing deformation gradient, right? And then at the end, I want to recover it because then I'm kind of subtracting that identity away, but the information is gone because I rounded it away. So this happens also in the first term and also in the second term. So we see that this is a problematic case when evaluating for small deformations. There are remedies to it, like there are some recent works to reformulate it, different mathematical expressions. There are also ways that you can basically write just an expansion around this dimensionless number, and in that Taylor expansion around that number will be then precise. But now I want to demonstrate to you that this framework is effective at measuring this. So I have here a strain energy density, and you see already that at the value of strain energy density there is a lot of noise. This is all rounding noise basically. And this is what I get as a rounding error bound. So I see that I only have bounded at some places. I cannot tell you that the error is better than 10 to the 8 relative error. So I already see that the plot that here it's really bad, right? It's noisy, and also the error bound is telling me that. And in case I implement the nice thing, the expansion around the small deformation regime, I recover basically the smooth picture, what I want to see. So this is the strain energy density for every cell. And my error bound now tells a much better story, that the quantity that I computed has a relative error not worse as 10 to the minus 11, which is, yeah, it's still pessimistic, still far from 10 to the minus 16 you would want to see. But this is because of the mode. If you would use even the more precise mode of measuring the error, you can get to the 10 to the minus 14. So just to summarize, we implemented this, should work for arbitrary UFL forms. You can just go ahead and measure how much a rounding error you are committing at what you already have in the code. You can check out the library where this is implemented, and yeah, that's the typical.
Thanks, Michal. Somehow you always seem to end up on that slide.
I always have to have that slide in.
Yeah. Quick question, Ridge.
Could you use this to talk about using less representations for some of the arithmetic? In other words, single byte, 2 bytes, 4 bytes.
Mm-hmm. Yeah. So
because that could speed up things, especially.
One of the future ideas, yes, especially with collaboration with Matteo, is to basically have more like a dynamic precision throughout the kernel. So this way you have local bound on every expression, and you can say, now I know this is precise. So maybe just to get on par with other things which are imprecise, I can spend less precision here, and then I can recover it back again. So that's the future work. Yeah.
Okay, cool. Make it automatic.
Yes, yeah, automatic.
All right, thank you, Michal. Let's give him another round of applause. And next week.